Thank you so much for the introduction. Hello, everyone. Welcome to my public PhD defense. It's a great pleasure for me to have you here, and I'm excited to present to you a summary of the work that I carried out during the past couple of years on the topic of computational mathematical modeling of the biodegradation process in metallic biomaterials. As the name suggests, it has a lot of details of mathematics and computing, but in this presentation, I try to avoid touching those details and stuff, and I will focus more on the big pictures and the reason behind the models and these kind of things. So let me first start with the importance and the definition of biodegradable materials, and for that, I draw your attention to a couple of examples from orthopedics. For fixation devices and implants, the implants that we put inside the body, we can categorize them into two classes of permanent and temporary. For permanent devices, they are supposed to provide a support for a long period of time, most likely till the end of the life of the patient, because they are going to replace missing functionality or for severe cases. But in most of the cases, for patients, the support is the needed support is temporary. And after fulfilling the mission, the implant is no longer needed, for example, after the bone is healed. And here an issue arises that an additional surgery is needed to remove the implant. But what if they disappear, vanish after they are done? And that's where biodegradable materials come into play. This is a clinical trial for a wrist fracture in which we have actually two types of fracture. One needs a permanent kind of fixation, and one needs a temporary fixation. For the permanent one, we use some stainless steel pins, and for the temporary ones, we have some magnesium screws. And as we can see, after 6 months, as the bone healing process goes on, the material starts to degrade, and after 12 months, when the process is finished, the materials is also not there anymore, which is really, really cool. For this, biodegradable metals, if we want to define them in a scientific way, as I said, the most important thing is they should dissolve and disappear upon fulfilling the mission. And this is, an electrochemical system. This is corrosion. But what is very important, a distinction, is that the response of the host should be considered as well, which is a biological system. The body, in vivo tests, all these things should be considered. But the good news is these materials can be also metabolized. So when the materials release, they are not dangerous, let's say toxic, and this is actually part of their definition. And there are a bunch of properties that should be taken into account when we are talking about biodegradable metals. And the most important ones are biodegradability and biocompatibility, and a proper material should have enough of the both worlds. But in addition to this, there are other material properties, like the mechanical properties, biological properties, chemical and physical properties should be considered. And proper material, biodegradable material to be called, should have, all of these things comprehensively. And by taking all these things together, we can say that magnesium, zinc, and iron are three metals that we can call biodegradable. There are metals that have great mechanical properties. They have a lot of application, especially for orthopedics and cardiovascular things. But the thing is, there are bunch of issues to tackle here. That's, for example, one of the issues is that the release profile of these materials should be tuned, depending on the application that they are undergoing. And this is where this PhD was defined. And the challenge that we had was that the biodegradation rate should be tuned based on the rate of the generation of the healing process for the bone or other tissues. And then the implant should be also optimized according to this, tuning. And the approach that we had to tackle this, to attack this issue, was to construct a mathematical model of the biodegradation process that can be later on, down the road, coupled with other tissue engineering models for tissue growth, for bone healing process, all these things, by considering the effects of the environment. And the way that this research is organized into a couple of objectives. The first objective was developing the core biodegradation framework. And later on, a couple of physics were added to that. The first one is the physics of perfusion. Perfusion is a term widely used in tissue engineering for when you have like a bioreactor that has hydrodynamics and fluid flow, because those are really common for in vitro tests especially. And then also the biology of the tissue growth and objective 3 that were added on top of the core computational model. And then since we did all these things in-house, like using in-house models and codes, we define also the objective 4 on code development, parallelization, and implementation. And then in objective 5, all these models were used in a couple of use cases. 3 of them are presented in the thesis for like material design, implant design, shape optimization, and these kind of things. The modeling workflow is very typical in like all these modeling projects that we have underlying phenomena being converted to mathematical models, and then mathematical models to computational models. For underlying phenomena, as I said, we have in objective 1 the chemistry of biodegradation, and objective 2 the physics of perfusion and fluid flow, and objective 3 the biology of the tissue growth. And for mathematical models, we converted these things into a set of like partial differential equations, mainly reaction, diffusion, convection. Also Navier-Stokes for fluid flow, and some interface tracking and capturing methods, because it was very important for us to track the morphology changes of materials that are undergoing corrosion. And for computational models, we had a combination of finite element and finite difference methods, parallel computing libraries, and open source solvers. So I start with the objective 1. That's where I spend most, the big portion of this presentation on the core biodegradation framework. And the model that we develop should capture, generally, a model of biodegradation should capture the dissolution of the material, in this case magnesium, as the thesis is also focused on magnesium. So the dissolution of the material, and then formation of products, like a kind of protective film on the surface, in this case magnesium oxide and magnesium hydroxide, and then also in the presence of certain materials, this, the breaking down of this narrow film, and also, increasing and decreasing the speed of degradation, as well as also change of pH, which is very, very important for us, especially in vitro studies. And then for constructing a mathematical model, as I said, we had like a set of partial differential equations that were describing these chemical interactions. They are mainly reaction, diffusion, convection. And an example of these equations that we have, like one equation per like contributing chemical species in the whole system. An example for magnesium can be written like this. That is nothing but a mathematical representation of how these ions are moving around, diffusing, actually in the medium, that get advected by fluid flow, like perfusion, and also interacts with other chemical like components in the system. So we have like one equation like this per component, and then we can model the chemistry behind in mathematics. But in addition to that, as I said, identifying the surface was very, very crucial for us, because that was actually one of the unique aspects of this research in comparison to other corrosion and degradation models, that we wanted to see how the geometry changes, like all the really clinical images that we had, like what happens to the implant when we put it inside a body or in a test environment. And for that, it was also mathematical representation of the surface. That was like we have a mathematical surface that moves with, we have the material releasing, and we have the move of the implant surface. And this is actually a very, very interesting topic. I will give you a very quick example of how we can define, how we can track actually objects using mathematics. One technique is using implicit surfaces. So we say that we have an object. In this case, the first example is a one-dimensional line, let's say. And we say that, for example, it can be defined using a function like this, x squared minus 2. And we say, wait, this phi function is 0. Those are actually the boundary of the objects. And when it is positive or negative, in this case, this is positive, that's outside of the object. And when it is negative, it is inside. So in this case, the object that we are investigating is this green line. If for any reason, biological process, chemical process, or anything else, this function changes, for example, x squared minus 1, we have actually the movement of the interface as can be seen here. The function is changed, so where phi is 0 is also changed. And as a result, we can say that this object has gone under like shrinkage, let's say. So this is actually the idea that how we can use mathematics to capture the moving of objects, the moving surface moving actually of objects. And it can be extended, the same concept can be extended to 2D, for example, in the square, where phi is 0 is the interface, when phi is negative, it is inside, so it's inside of the circle, and when it's positive, outside. And if the function changes, even the shape of the circle can change, and we can track what is happening to that. So here we need a function like phi describing chemistry, undergoing chemistry, and can be used to say that, yeah, this is the object of the implant inside the test environment. So we have actually implicit tracking of the corrosion front. And for that, there are a bunch of techniques here. And one is level sets. That gives us actually the phi function. So we have the phi function that is linked to the underlying phenomena. We plot it, and then we see what is happening to the morphology and the geometry of the implant. So the way that we can describe it is like we have the block environment. We know that we have a shrinkage velocity. If we zoom in, we have like a concentration gradient. And this is the equation that it gives us. The equation can be a little bit scary. That doesn't really matter. In the end, we solve it. But the nice thing is we have a phi here. So we solve this equation, and then we have phi. And as a result, we can also see what is happening to the morphology of the object. So we can say, for example, for an orthopedic screw, where phi is 0, it's that's the interface. When phi is, for example, negative, it is in the medium. As I said, it doesn't matter really, positive, negative. And when it is, for example, positive, it is inside. So this is when the mathematical model is completed, and we can move on to construct the computational model, solve all these equations. So the PD is describing chemistry, and the level set equation to track the changes of the morphology. And all these things, because of the coupled system, that was not feasible to implement in like commercial tools, like in tools with pre-built models like COMSOL, ANSYS, or Abacus. And as a result, we decided to implement it by discretizing the PDs using finite element method. The accuracy of the interface on the interface is actually very important for all the PDs and stuff, like the mathematical things. And as a result, we needed to refine the mesh, the finite element mesh, on those regions. And this is actually where those heavy computations comes into the whole work, and parallelization and all those things. But here, what is really important that I want to show you, like the typical mesh that we have for the screw that I showed you, then this is a way that we refine a mesh on the interface to increase the accuracy. So this is an example in 2D, and this is the same example in 3D, screw placed inside like a kind of cylindrical container. So for all the things that I will show you from now on, this is the mesh behind the scene. And then the next step is the verification of the code as it is in-house. And for that, we had like a kind of qualitative and visualization inspection. The first aspect is that those PDs that I said, describing the system. And then we want to see how the mass loss works. This is the same screw that I showed you. This is a release of material, as you can see, and also shrinkage of the screw as a result of biodegradation. And the next thing that is also very important is a level set tracking of the surface movement. And here we have like a blue curve, which is nothing but the 0 isocontour of the phi function that I showed you. And we can ask the post-processor visualization tool, in this case that's ParaView, to plot where phi is 0 over time, and this is the result. So this is a way that all these things can be used together to model biodegradation. And this is another example for porous scaffold. On the left, we have like side like as I said, the formation of the protective film, and on the right, that's the release of material, and also the shrinkage of the surface. And the next, and probably the most important step, is model validation. For that, we had like some experiments being done by our partners in Germany that were immersion tests in simulated body fluids, so buffered solution and also saline solution, really harsh, let's say, corrosion environments, and measuring mass loss via indirectly by the formation of hydrogen, as they are equivalent. Some stoichiometry is needed, but they can be converted by gathering the release hydrogen, and then it can be a live monitoring criterion for mass loss, and then also measuring pH that we used, global pH that we used to validate the models actually. So we use like the mass loss data to calibrate the model, to estimate the parameters, model fitting kind of, but then we used like local global pH as a criterion to validate if the model works correctly or not, if there are agreement between experimentally obtained values and computational predictions. So this is the same setup. In this case, all those chips, metal chips, are combined into one surface, considering the surface to volume ratio. And then the degradation in the first 21 hours is simulated and also experimentally tested. And this is a finite element mesh that contains around 80 million elements because of the refinement on the surface. These are, a glimpse of results, the same results being visualized in two different ways: degradation and release of material, and the surface that is evolving. And also, as I said, the change in global pH that's used later on for validation in low diffusion, buffered solution, simulated by the fluid, let's say, and also in high diffusion regimes in solid solution, really like harsh conditions. Yeah, we have like a higher pH. These are some quantitative results. I don't want to show you a lot of quantitative things here, but here you can see that we have a very good agreement between the results, between experiments and the computational results for the predicted pH changes on the surface of the implant, of this, this narrow magnesium, let's say, plate. And then from that point, there were different directions that we could go for, and like trying to capture more complex chemistry or investigating the effect of alloys and more complex material interactions, all these things. But instead, we went to another direction that was complicating the chemistry in order to see if we can capture more chemistry actually happening very close to the biodegradation surface. And that's what, I don't want to go to the details of this here. It is elaborated in the thesis. But for that, we coupled the code, the kinetic biodegradation model with the thermodynamics model with some simplification. And then we managed to predict, to replicate the same results that were obtained, again, from same partners in Germany, using the setup that you can see here. But one important thing regarding the setup that is depicted here is the addition of perfusion or hydrodynamics in the terminology of corrosion and chemistry. That we have inlet and outlet of the solution, and as a result, our model should be able to capture this. And that's where the second objective comes, adding perfusion models. So the effect of convection, this is very trivial, but I have a visualization here for the effect of convection. What happens when we apply convection to a system? So these are two finite element simulations with pure diffusion and diffusion convection. So when we have a fluid flow, in this case from left to right, it actually advects the released material. In this case, it can be temperature or concentration or anything else, like any scalar value, to the direction of the fluid flow. And this is exactly what we want to be added to the biodegradation model. And for that, we need to deal with Navier-Stokes, which is, as I said, very trivial. And for a couple of technical reasons, we couldn't use available CFD codes, fluid flow codes. So we decided to implement our own, finite element solver in this case. That was not a solver, but I mean a code to solve Navier-Stokes equation ourselves in order to couple it and without sacrificing the performance of the models, biodegradation model. And the code is also shared in GitHub. And then what was really, really important was comparing again, verifying that the developed CFD code works correctly. In this case, we compare the output with other like known CFD solvers out there, probably one of the best ones. And then the last stage was couple all these model, like fluid flow things with the biodegradation model. So we needed to reproduce the geometry of the chamber. This is a finite element mesh. And then this is a comparison of the results of the code we had inside, like a flow inside the chamber. Same setup being simulated in a code that we developed and OpenFOAM, showing very, very similar result qualitatively, and as we zoom, also quantitatively, very, very similar results. So that was for verification, but the next stage was adding like biodegradation to the model, so the effect of biodegradation to the fluid flow model, and also effect of fluid flow to the biodegradation model, which was actually the term that I showed you, convection term in the PDEs. So this is an example that instead of the hollow, like a boundary condition, we have a real degrading object inside the tube, let's say, a pipe, that you can see that it releases ions in this case are advected to the right. And there is another example here that is for, kind of exaggerated, very high and harsh diffusion regime, that we have the advection and release of material, the release material advected to the right. And as you can see, also the degradation is directional. We have more degradation on the faces, the face is normal to the direction of the fluid flow. So that was objective 2, more or less. And then, as I said, we use all these things added to core computational model in objective 1 in order to predict the chemistry of degradation close to the biodegradation surface. And then for objective 3, it was like the tissue growth model, biology of tissue growth. That was considering what is happening for cell proliferation and also new tissue formation when we have it on top of biodegradable materials that can be later on coupled for like bone healing processes, especially for large bone defects. And for that, we had computational models of this process. I had also a very, very interesting line of research in the hospital branch of the team, experimentally investigating this, but this is the computational branch. So modeling growth, very similar to what I showed you for the interface. Again, capturing the interface as a mathematical object and see what happens. So in this case, it is, instead of chemistry behind the scene, it's biology. And then it was important to couple the biodegradation and tissue growth models together. This is an example of the model that we are seeking for. This is an example that was implemented a couple of years back in the group. And this is using level set. The model had a couple of things regarding the objective that we had, and as a result, we decided to implement it using another technique, so not level set, and another one. But the thing is, the way that these models work is based on a fact, proven fact, that new tissue grows faster in regions with higher curvature. So if we see like cells on the circumference of an object, in this case, for example, this is square. As you can see, as the arrows show, the speed of the growth of the tissue is higher in the regions that the curvature is more. And in order to capture this, there is another interface tracking method called phase field that is very similar to level set, but instead of like having the phi function being defined negative, positive, and 0, it says that it's +1, -1, and the transition between -1 and +1 is actually the interface. So it gives us an equation, we solve the equation, and this is the way that we can see where the tissue goes and what happens during the growth. These are very, very preliminary results of that model, just showing that the model works. And then we had also comparison, the same model implemented in level set, and comparing these results, seeing what happens, and also having the growth on more complicated geometries like TPMS, like scaffolds and these kind of things. And then it was also important to have like the tissue growth on the degrading scaffold or degrading objects. And this is actually where a big problem happened, that we have like the scaffold and the medium. And as I said, this is here, psi is a 5 function of the level set. It's the same thing, positive, negative. And then also for the phase field, we have -1, 1 tissue on top of the scaffold. As the tissue grows, we have also the scaffold that degrading. And then we have a new mathematical region appearing there. Actually, we had some problem implementing this. And this is a very controversial, actually, figure that I think we spent half an hour on this in the preliminary defense about like this, discussing the details. There are a bunch of solutions to that, using more advanced, for example, phase field models and mathematical models, or completely forget about like these kind of growth models that we had and focus on something else. And that was actually the PhD work of Lise, later on continued by Arlie, and now is being continued by Lara, that they are actually can be easier to integrate into the biodegradation framework. And then we had also discussed if it is really necessary to consider this. But our problem was also validation of these models. So this is still an open question. And in the end, we didn't manage to implement this part. But all the details of the reasons and also the tissue growth models are elaborated in the thesis. And then objective 4 is related to code development and parallelization. This is actually my interesting part of the thesis, but I'm not going to elaborate on this here, as I promised. So for the software development, all the codes, all the models that we developed are encapsulated in a software we call BioDeg, multifunctional 3D simulation for corrosion and biodegradation simulation that features also a cross-platform user interface. And cross-platform here means that it is capable of being run on different operating systems. And it is available in release as an open source tool. And although this is very, very special software for a very specific part of science, we had also a couple of users working with this that is able to, enabling them to study corrosion and biodegradation for any arbitrary 3D shape. But in addition to that, another interesting thing here is as the numbers said, for the millions of elements in finite element computation, we really need parallelization in order to increase the performance and decrease the simulation time in order to make them feasible turnaround time for performing investigations. And for that, we had a couple of techniques. The first one was distributing a mesh, the domain into available computing resources, like domain decomposition, that we decompose the mesh into different partitions. In that case, it is for example, 2,000 partitions, and then just assigning each partition to one CPU core, so that with 2,000 CPU cores, we can have actually the simulation in parallel. But in addition to that, that was also important to consider that in the end of all these finite element simulations and stuff like that, in the core, we have a linear system like this. So it is really important to understand the system and trying to increase the speed of calculation for finding the solution of this system. And one good approach for that is actually preconditioning the system. So this is really a quite old mathematical approach that we precondition the system, and then using an iterative solver that are really fast, especially in parallel machines, we can have really faster simulations. So as I said, there are a bunch of details here, but I'm not going to touch them. So I go directly to objective 5 for applying the model for a couple of applications. The first application is related to patient-specific porous implant, the work that combining biodegradation model with the work that was carried out by my friend Fernando. That was in this kind of for large bone defects, when we have the acetabular implant, there is a patient-specific part in the back that can be made from biodegradable materials. And for that, we can have like some topology optimization or just simply like geometry construction from CT images. And in this case, we wanted to see what happens to that part from the biodegradation perspective. In order to simplify it, we just assume that there is a cup on top of the liner, in this case polyethylene liner, that is made from biodegradable material. But later on, the whole workflow can be applied and can be extended to real CT images and more complex geometries. So this is the output of the surrogate modeling, as I said, performed by Fernando. And then we have a biodegradation, so putting this detailed geometry into a container, generating the mesh, and then having the biodegradation simulation on it, showing that degradation happens faster in regions that are more porous and slower in the more dense regions. But as I said, the whole workflow can be applied immediately to more complex geometries. The application 2 was related to mechanical integrity of infilled structures, a work that we did in collaboration with the University of Kyoto. These are like the typical examples that they had as a result of topology optimization, and then they wanted to see what happens to these structures when they undergo biodegradation, especially for biomedical applications. And we also wanted to consider the effect of biodegradation in the topology optimization routine. So this is an example of the topology optimization. So we have a fixed boundary condition in this like a block of material and applying load, and then based on two different constraints for topology optimization, we can have different shapes. This is the way the topology optimization works, starts to remove materials based on the constraint and giving us an optimal solution for where the material should be. And then later on, we use this inside the biodegradation framework, yielding to something like this, to investigate what happens to the mechanical strengths of these materials when they undergo corrosion and biodegradation. And we are still, this is still an ongoing project, let's say, with Hao, my friend from Japan, to include the effect of biodegradation back into the topology optimization. And the objective, the application tree work we did, as the output of the biodegradation model on the, in collaboration with a friend of mine, Peter, that was reading the output of the biodegradation. So this is really offline coupling into a tissue growth and also a mechanical, solid mechanics model, let's say, analysis model, in order to see what happens to the strengths, mostly like the ultimate testing UTS point of for the material in tests when they are biodegradable and they are placed into the really gel, especially when a mechanical force is applied, and in this case that was biting. So the model had 20 million elements, the biodegradation model. This is a glimpse into the results of the biodegradation, very similar to the previous ones that I showed you. Release of material and the shrinkage of the surface. And then on top of that, we had also mechanical analysis showing what happens to the force displacements or stress strain curves over degradation. And we had also a simplified tissue growth model on top of that coupled in order to see at which point actually the strength of the material falls below the strength of the growing tissue. So, in the end, I want to finish the presentation with emphasizing the importance of open science and open source in this project. All the tools that we use in this project, they are open source and freely available. And it was actually literally impossible to create these kind of really detailed models, mathematical and computational models, without the power of open source tools. So this is really something that I'm very proud of, let's say, and for these tools actually, that they are really, really powerful, although they are usually underestimated. But that was also very important for us, in line with the same philosophy of open source. Follow the same thing for open science. And one of them was trying to document and publish the building blocks of the project. So trying to decompose the project into smaller pieces and document and publish them to the community in order to increase the reproducibility and also increase the transparency and outreach of the models. One example here is related to like the parameter fitting or parameter estimation of the models that were published in the Journal of Open Source Education. But there were also other components. As I mentioned, the fluid flow code is also published on GitHub. And the tissue growth will be published soon, and really smaller building blocks instead of the whole. The whole model is also published, is shared and freely available, but also the building blocks. And also on top of that, we had some science outreach projects going. So really like sharing the details of these techniques and models in a simplified language. An example of which is computational mass transfer in tissue engineering. That was actually a course taught by Hans. And then we started to convert part of it to set of Jupyter notebooks, for example, and then sharing them with the general public on GitHub. Also, for example, another example is an introduction to applied numerical computing. That is also a set of Jupyter notebooks for really simplified language of, for example, finite element, finite difference, and mathematical modeling, computational mathematics as well. And there was another project that was a direct output of this PhD project. I think most of you already know this. That is a project called ToxRiders, showing as I said, the power of these open source tools, as well as the details of the computational and mathematical like models in a simplified language on YouTube. And I'm really happy about a community that is now formed around this, and like the interaction that the users they have like with me and with each other. So it's really like also growing. So as a general conclusion, I would say the output of this PhD is a multiphysics, mechanistic, multifunctional model in order to investigate the biodegradation behavior of metallic biomaterials with a focus on magnesium in silico. And then the model was also implemented in a way that was very important to be able to be plugged with other tools, with other models, and with other codes. That was very important, interoperability of the models, let's say. And then a lot of details of the like mathematical modeling of these moving interfaces are elaborated in the thesis for both phase field and level set methods. Also parallelization of these these models. And as I said in the beginning, the high-performance computing and open source workflows were very important in building the models that I presented in this presentation. And as a final word and acknowledgement, I want to thank all the collaborators, and especially external collaborators from different universities around the globe. And also lovely people that helped me a lot in my work, without which, for sure, this PC was not possible at all. The photo on the top is the BME generation that I feel belong to. And the photo on the bottom is a very recent lineup of our research group, and by very recent I mean that I'm not there anymore. Thank you so much for your attention.